This video is going to introduce us to the basic concepts of how we go about predicting the stability of an organic molecule. We're not going to get into specific examples in this video. That will come in the subsequent videos. This is just going to be an overview because this is a pretty big concept. So when we are predicting stability of an organic molecule, we are going to look at 4 factors. And when we look at these 4 factors, we look at them in order. So that means that we start by looking at the first factor, factor number 1. And if that factor does not help us predict stability, then we move on to the next factor. And if that one doesn't help us make a prediction, then we move on to number 3. And if that doesn't help, we move on to number 4. The first factor that we use to predict stability is analyzing the atom, and I'm going to do this color coding here for a particular reason. We're analyzing the atom or atoms in the molecule with a formal charge. So in this analysis, we're going to be asking ourselves, first of all, do any of them have formal charges? And if any of the atoms do have formal charges, we're going to look at that formal charge and determine whether or not it makes sense. And that's going to depend on if it's a positive formal charge or a negative formal charge. And we've already talked about this a little bit when we talked about analyzing good resonance structures versus bad resonance structures. So for example, if we have a negative formal charge, we want to see that negative formal charge on an electronegative atom. And if we have a positive formal charge, we don't want to see it on an electronegative atom. So a lot of times the atom with the formal charge is going to be all that it takes for us to determine the stability of a molecule. I would say probably 95% of the time, this is the only thing that we need to consider. But occasionally we have to go deeper. Maybe when we're predicting stability for whatever reason, the formal charge doesn't help us. And so in that case, we move on to factor number 2. And with factor number 2, we're going to be looking at resonance structures. And for this analysis, we are literally just looking at the volume of resonance structures. How many are there? The more resonance structures a molecule has, the better it is, because resonance structures help, as you know, they help spread out formal charges, they help spread out electron density, and things like that. So the more resonance structures a molecule has, the better and more stable it is. And if for whatever reason, actually for pretty much everything, I would say 99.5% of the molecules that we work with, those 2 factors are going to be enough for us to determine stability. But if for whatever reason we cannot determine stability with the first 2 factors, then we move on to factor number 3, which is induction. Induction, in this case, due to electronegative atoms. We haven't spent a lot of time talking about induction. Induction is really similar to electronegativity. It is kind of the dragging of electron density across the molecule due to some sort of polarity somewhere in the molecule. And when we go on in the next couple of slides, we'll look at a lot of examples of induction. So if this feels kind of hazy to you right now, just stay with me, not just in this video, but in the future videos as well. And I would say pretty much 100% of the time, these 3 factors are enough for us to determine stability. But just in case, we have a 4th factor. And that 4th factor that we will look at when we need to is the orbital shape of an atom with a negative formal charge, assuming that we have one. Now, the reason that I've color-coded this in the way that I have is because we have this mnemonic, this trick, to help us remember these 4 factors in the correct order. ARIO, A-R-I-O, which helps us remember atom with the formal charge, resonance structures, induction, and orbital. Now, I can't take credit for inventing ARIO. That was invented by textbook author David Klein, but it's an amazing tool that works all of the time to help us predict stability. Now, when we're doing these predictions, in order for ARIO to really work effectively, there's a couple of conditions. And again, I want to make sure you know, not exceptions, because this always works. These are just some conditions. So ARIO works better when we are comparing multiple molecules, like 2 or more molecules. It's a little harder to use ARIO when we're just looking at one single atom. So this is best when we are ranking or comparing 2 or more molecules, and we are saying, of this set, of these 2 molecules, which one is the most stable? So this is ideal for comparison because it's better at helping us predict, of these 2, this is the most stable. It's a little harder for us to make predictions about how stable the molecule is, but it's good for helping us predict which one is the most stable. And another factor, another condition when we're using ARIO is that sometimes when we're looking at the stability of molecules, we're comparing them, sometimes it's more helpful for us to actually compare and analyze not the molecules themselves, but their conjugate bases or their conjugate acids. We'll just say conjugate bases. So sometimes when we're doing this, we are going to actually compare not the molecules, but their conjugate bases. And less likely, maybe we would be comparing conjugate acids. And don't worry, if you're feeling like, oh my gosh, I don't know what she's talking about, we'll do examples of this. But so sometimes when we're being asked to rank stability or compare stability, it's easier for us to actually compare the stability of the conjugate acid or the conjugate base of these particular molecules. And if we have to resort to that tactic, we have to remember from Gen Chem, our strong acids, which is another way of saying unstable acids, or reactive acids, turn into weak bases, which is another way of saying stable bases, non-reactive bases. So sometimes when we have to do these comparisons, we have to actually look at the bases instead of the acids, rank them, and then turn that ranking around, reverse it to apply it to the acids, because the stability of a base is opposite of the stability of its acid. And the same is true if we want to replace acids over here with bases and replace these bases with acids. The same relationship is true. A strong base produces a weak acid. An unstable base produces a stable acid. So let's look at some examples, because you really need to see this in action to really understand it well.